I'm very happy and honored to be here. And so if the overarching question of this workshop is why the Everett interpretation is not the consensus, I think there's a very serious problem that most people underestimate, and that has been the focus of some talks yesterday. How do you recover any worlds, any recognizable empirical content at all from the quantum state or the wave function alone? But I will, of course, bracket this issue and try to make a more optimistic and constructive contribution to the many worlds program by arguing that with respect to another issue, the so-called probability problem, the many worlds theory is in a better shape than most people think. And in some sense, it's going to be a very conservative and modest talk. So I'm going to make the case that the original account that Everett provided was already pretty much right, at least as good as it gets. And on the other hand, it will be a somewhat provocative talk because I'm also going to make the point that most people, including, or maybe especially, most followers of Everett didn't really understand or appreciate what Everett did. So what is the probability problem that I was referring to? On the one hand, it's simply the question how to justify the Born rule in the many worlds theory. So just recover the statistical predictions of textbook quantum mechanics that, as we all know, are extremely successful. And then the somewhat deeper question, what do probabilities in an Everettian multiverse even refer to in the first place? What does it mean to speak about the probability that a certain measurement outcome occurs? For instance, if, according to the theory, all possible outcomes will occur with certainty. Right? And we all know that naive branch counting doesn't work, like the idea that the probability of an event is just, in a naive sense, the relative frequency of worlds in which this event obtains, either because it yields the wrong statistics or because under decoherence-based or otherwise more sophisticated understandings of the many worlds theory, there's maybe no well-defined number of branches, number of worlds in the first place. So because it seems hard to locate interesting probabilities as objective probabilities in an Everettian multiverse, many people try to locate them in some sense in our mind, i.e. That is, interpret them subjectively. And the proposal I understand best has to do with self-location uncertainty, as in Lev's Sleeping Beauty problem. So simply put, after you perform a measurement, but before you look at the device, what should your credences be to find yourself in a branch in which the result is A versus B? And then there is, of course, also the Deutsch-Wallace program, which takes a more decision-theoretic perspective and tries to argue that we should compute expected utility based on the Born rules, and this should guide our actions, and so on and so forth. And of course, we could have an entire conference just about like subjective versus objective probabilities and different interpretations. But I think these accounts are ultimately missing the point, right? What we want to explain are very concrete, empirical, statistical facts that the theory has to account for. So what is at stake is not, we don't have to explain in the first place like the beliefs or betting behaviors of physicists, but very concrete empirical facts that the theory must account for. Otherwise, the theory cannot be considered empirically adequate. And again, I'm going to make the case that Everett gave already a very good explanation of an objective notion, account of an objective notion of probabilities in a many worlds theory that does justify the Born rule. And Everett, to understand and appreciate what Everett did, we must first understand what Boltzmann did, because Everett makes essentially Boltzmannian arguments. Right, so let's look, for instance, at Boltzmann's statistical mechanics and how Boltzmann explained the Maxwellian velocity distribution as an equilibrium state of an ideal or weakly interacting gas. Right? So here's a quote from Boltzmann. He explains the ensuing most likely state, meaning the equilibrium state, is not an outstanding singular state, opposite to which there are many more non-Maxwellian velocity distributions, but it is, to the contrary, distinguished by the fact that by far the largest number of all possible states have the characteristic properties of the Maxwellian distribution, and that compared to this number, the amount of possible velocity distributions that deviate significantly from Maxwell's is vanishingly small. Then he explains the criterion of equal possibility or equal probability of different state distributions is thereby always given by Liouville's theorem. Liouville's theorem, of course, establishing that the standard Lebesgue measure or the induced microcanonical measure on a hypersurface of constant energy is a stationary measure, so conserved by the Hamiltonian dynamics, right? So if we look at a gas in a box, the gas has a well-defined microstate, right, that determines all its physical properties and follows precise deterministic laws, right? Then we can look for each microstate just as the empirical distribution of particle velocities, right? So basically we just look at the relative frequencies, the proportion of particles in the gas whose velocity is in a certain small interval, right? And then one finds that for the vast majority, for nearly all possible microstates of the gas, right, the empirical distribution of particle velocities in the gas is approximately a Maxwell-Boltzmann distribution, right? And here, this mu is a measure on phase space, right, on the possible microstates of the systems, typically the Lebesgue or the microcanonical measure, right? And there are many different ways to make technically precise what it means that this empirical distribution is close or approximately equal to a Maxwellian distribution, for instance, as follows, but one could also consider, I don't know, Wasserstein matrix or bounded Lipschitz metric as a distance of these distributions, right? So the statement, the result, the explanation of Boltzmann is that for an overwhelming majority of possible microstates, the velocity distribution of the particles is approximately a Maxwellian distribution, or Maxwell-Boltzmann distribution, if you want. Right, and now it's extremely important to appreciate that there are three different measures involved in this statement that are technically probability measures, at least if you normalize the Liouville measure, which you don't have to, but if you do, they are technically probability measures, but they all have a very different status and meaning. First, we have the actual empirical distribution of velocities as a coarse-graining function of the microstate, right? So each possible microstate of the gas just determines the statistics of particle velocities in the gas. Then we have the theoretical Maxwellian distribution, and then we have a measure on phase space, which I'm going to call a typicality measure, in this case the stationary microcanonical measure, right? And the role of this typicality measure is just to give us a reasonable notion of what it means that an overwhelming majority or nearly all possible microstates have an approximately Maxwellian distribution. So essentially this measure on phase space is only used to identify very large or very small states, right? And again, then the statement is that for an overwhelming majority, or for nearly all possible microstates, the empirical distribution of particle velocities is approximately Maxwellian. Let's look at another example, still in the context of classical mechanics, that gets us one step closer to where we want to go. And it's one of the favorite examples of my former teacher, Detlef Dürr, who sadly passed away last year. Tim has also a paper that discusses very nicely the Galton board. And you know the drill, you know the Galton board, so you throw in particles, they're in a receptacle, and then they pass here a number of pins, and each pin, a particle can go left and right, and then here they end up in these columns down there, and if you do this multiple times, you will find a binomial distribution of balls or particles in each of these columns. And of course, this is a perfectly deterministic process. So for any initial condition of the system, the classical dynamics determines a unique trajectory and determines deterministically where each ball will end up. And now let's think of this Galton board like as a model of our universe. So we live in a Galton board universe, and we have one initial condition for a large number of balls at an initial time that are just fixed up. The system is perfectly isolated, and from there on, everything runs its deterministic course. Right? So this one initial condition of our Galton board universe determines completely the distribution of balls that end up in this receptacle at the bottom. Right? And then we have again a typicality measure on phase space, right? On the space of possible initial conditions of the system. We have the empirical distribution of balls, so which fractions of balls end up in each of these columns. So think of n as the number of columns, which is completely determined by the microstate of the system. And then we have the theoretical binomial distribution here approximated as a normal distribution. And again, the statement, which can be very hard to prove, depending on how detailed one wants to model this Galton board, is again that for nearly all microstates, nearly all possible initial conditions, the empirical distribution will be very close to a binomial distributions. Right? So here the good initial conditions basically correspond to this big blue set of microstates, and those microstates for which the empirical distribution deviates significantly from a binomial distributions. For instance, all balls end up in the leftmost column. They have a very small measure. Right? And what do probabilities refer to in this understanding? So probabilities, the probabilities that in this case Newtonian theory predicts, are typical relative frequencies. Right? So probabilities are relative frequencies that obtain for typical initial conditions. So for most or the overwhelming majority of possible initial conditions. If you don't want to think about the binomial distribution here in the receptacle, you can also say that the theory predicts that for the vast majority of possible initial conditions, the ball that goes to the board, the relative frequency of the ball going to the left of a pin or the right of a pin is approximately 1/2. Right? If it goes to a large number of pins. So you have typical relative frequencies as a function of the microstate. So you don't smuggle in any sort of beliefs or ignorance or knowledge. It's just an objective statement of the theory that almost all, or better, nearly all possible initial conditions of the system will show this statistical distribution. Right? And we saw already in the Boltzmann quote, he still mixes sort of probabilistic language with typicality language, talking also about the most likely state. But this probabilistic talk on this level really doesn't do any work. And then there is like a really more modern concept of typicality that has been worked out by many people here, just some of them. And I'm just giving you a very flat-footed version of that. So just a feature of our world is typical if it is a feature of nearly all possible worlds that the fundamental theory, the fundamental laws allow. And here in the classical case, the possible worlds is essential. It's a modal way of reasoning. We reason about what is the case in the vast majority of possible worlds. I put it in quote that, of course, in the Everettian context, we will have an ensemble, we will have, let me not say ensemble, but we have a Gesamtheit, what's the English word, of actual worlds. And then typicality is associated with a rationality principle. For this formulation, I'm drawing a lot from Tim, actually, that if a feature of our world is typical according to our theory, there's just nothing left to explain. It's just irrational to wonder further why our actual world is in that particular respect like nearly all possible worlds that the theory describes, that the fundamental laws allow. But if a somewhat salient, interesting feature of our world is atypical, those are in general exactly the features that cry out for further explanation, right? That strike us as puzzling. And in the last resort, those are also the kind of observations that might severely challenge or falsify a theory. Like if you think, for instance, that the double-slit experiment falsifies classical Newtonian mechanics, well, it's not possible that in a Newtonian universe you find the initial conditions are so special that whenever you shoot particles through a double slit and record them on a screen, they create they create an interference pattern. Nothing about that, strictly speaking, violates Newtonian laws. It's just atypical, right? So here, again, there's much more subtlety to that, in particular also about what exactly is the difference, further substantiating the difference between probability and typicality. But here, typicality just refers to what is the case for most possible initial conditions. So it's just about very large versus very small sets of possible initial conditions. And the same concept and the same Boltzmannian types arguments are also used to derive the Born rule in Bohmian mechanics. But now let's finally come to Manuel's and Everett's typicality argument. Right? So Everett understood very well, I think, what Boltzmann did, and he even uses very explicitly, and quite remarkably so, the typicality language. So he says, we wish to make quantitative statements about the relative frequencies of the different possible results of observation, which are recorded in the memory, for a typical observer state. Right? So for the kind of frequencies that a vast majorities of observers in the multiverse would record or would experience. But to accomplish this, we must have a method for selecting a typical element from a superposition of orthogonal states. The situation here is fully analogous to that of classical statistical mechanics, where one puts a measure on trajectories of systems in the phase space by placing a measure on the phase space itself and then making assertions which hold for almost all trajectories. Right? So exactly the Boltzmannian argument that I just summarized in the typicality language. However, for us, a trajectory is constantly branching, transforming from state to superposition with each successive measurement, and one can add also with natural processes that are going on all the time. To have a requirement analogous to the quote-unquote conservation of probability, remember Boltzmann referred to the Liouville theorem, the stationarity of the measures, the criterion for the typicality measure. In the classical state, we demand that the measure assigned to a trajectory at one time shall equal the sum of the measure of its separate branches at a later time. This is precisely the additivity requirement which we imposed and which leads uniquely to the choice of square amplitude measures. So this is from his 1957 paper, but most of it appears almost basically verbatim also in his PhD thesis. Right, so what is this additivity requirement that he refers to here? So Everett did basically exactly what David asked of Simon, just state the criteria that uniquely determine, in this case, the typicality measure, and Everett postulated three criteria of assumption. First, that the typicality measure, the way of determining what do we mean by a great majority of branches or worlds in the multiverse, should be a positive function of the complex values coefficient associated with the branches of the superposed wave function. I mean, here it could also be the coefficients to the power of 0, so it could still be constants if that makes sense. But reasonable assumption, what else would you use? And he said it should be a function of the amplitudes of the coefficients alone, because the global phase is not well defined. Here maybe one could say, well, why not use a measure that has something to do with, that somehow depends on the relative phases between the branches. So maybe not an airtight requirement, so to speak, but a very reasonable one. And then comes the additivity requirement. If a branch B is decomposed into a collection of sub-branches, then the measure assigned to B should be the sum of the measures assigned to the sub-branches. Right? And this is exactly looked like diachronically what Everett describes as equivalent to the stationarity condition in classical mechanics. Right? And so this means that at one time the weight associated to a branch B is always the sum of the weight assigned to the sub-branches that result from it. Right? And this implies exactly that it doesn't happen what Simon showed in this talk, that here suddenly the weight, let's say, of the lower branch suddenly jumps from 1/2 to 1/3 or something like that. So here we have something analogous to the conservation of the measure, in this case, just by the unitary Schrödinger dynamics. But this additivity requirement is maybe even more important if we think that the notion of a world branch is vague, right? That there is no well-defined number of branches, right? That there are different ways, more fine-grained or more coarse-grained one, to look at the wave function in quantum state and say which parts are approximately decoherent and correspond to a different world, right? So this is like my illustration sort of a wave function. And here we could say, well, there's one branch in which the result was spin down and one branch in which the result was spin up. But we can also take a more fine-grained look and maybe say, well, there are really here two worlds in which the result was spin down, and here there are three worlds in which the result was spin up. In either way, we want to slice this wave function or quantum state into world branches, right? This additivity requirement assures that the total weight assigned to branches in which the result was spin up or spin down is consistent, right? Even if the branches are vague. So that was not something that Everett stressed. I suppose he thought of the branching process more or less as a discrete, precise thing. But it does great work, this requirement, in what I consider the most sophisticated understandings of like decoherent-based versions of many worlds and so on. In any case, we have these assumptions on the typicality measure. And now we consider, for instance, just as a special case, not as a perfectly general derivation or justification of the Born rule, a spin measurement on an ensemble of n particles prepared in the identically spin state here. Alpha times spin up and beta times plus beta times spin down. And then we can consider here the branching of the many worlds history. Again, simplified, it's consistent even if the branches are not well defined. After, let's say, 3 iterations, here the splitting into history. And then, of course, now it's simple combinatorics, but it's also really just simply the weak law of large number for, in this case, for a Bernoulli process. So what is the total weight of branches in which spin up was registered k times, right? Again, simple combinatorics. And then it follows that what is the total weight of branches in which the relative frequency of spin up is roughly equal absolute value of alpha squared. Well, it's almost full measure for large n. Right? That's in this case simple combinatorics. In the general case, is just mathematically the weak law of large numbers. Right? So the result is that in nearly all branches, spin up is registered with a relative frequency approximating the Born probability. In this case, absolute square of this coefficient alpha. Right? And if you think about it, in some sense, this result is optimal. We know that Born statistics, they cannot hold in all many worlds histories. Right? There are some branches in which spin up comes out every time or never, right? We know that according to the theory, these branches exist. So the best you can hope for, of course, is to show that Born statistics hold in almost all branches, or nearly all branches, doesn't have to be exactly measure one, with respect to a reasonable notion of nearly all. And the reasonable notion of nearly all, the criteria for that is what Everett stated as the assumptions on the typicality measure, right? And again, so what do probabilities in an Everettian multiverse refer to, right? As in the typicality story for classical mechanics, objective probabilities are relative frequencies along typical branches, right? Are the relative frequencies that hold in most branches of the multiverse, right? How do we justify the Born rule in the many worlds theory? Well, Born statistics hold in the great majority in nearly all or along nearly all many worlds histories, right? So it's important also that these objective probabilities are not assigned to singular results. Those are the typical long-term frequencies across the multiverse, the long-term frequencies that hold at least approximately in the vast majority of branches, right? So in what sense does this or does this not solve the probability problem? Now one may want to conclude now from this analysis a concrete prediction. Well, if Born statistics are typical, so I should expect to experience a history consistent with the Born rule, with the predictions of textbook quantum mechanics. But of course this is tricky because we know that in the many worlds theory there will be many future versions of me, many successors of me, or at least some, not many, but there will be successors of me that will experience, if they survive at all, statistics that are very different from Bornian ones, right? So future histories in which standard quantum mechanics is false, right? And I don't know how to get around the fact that many worlds theory lacks a certain predictive quality in this sense. I think this is an issue, but probably tied into many other deep questions about personal identity and the relationship between my present self and my future successors. But I think this is an issue that Everett's account doesn't solve, right? We can't really conclude with a prediction, so you should expect to experience statistics or phenomena consistent with Born statistics. But I think that the theory with Everett's accounts can at least successfully ground post factum explanations, right? If we look back and wonder why have we experienced a history consistent with Born statistics, consistent with the Born rule, then the answer is, well, because the Born rule holds in the vast majority in nearly all many worlds history. So I think that Everett's account succeeds in that sense. And now, of course, the standard objection that has led to, I guess, rejecting Everett's account is that it is in some sense circular or question begging. So here is a nice formulation from David Wallace's book, but it's just a good, nice formulation of a general sentiment, of course, that many people have, not to single out David, who says that Everett, in his original paper, proved that if a measurement is repeated arbitrarily often, the combined Mont-square amplitude of all branches on which the relative frequencies are not approximately correct will tend to 0. And of course, this is circular. It proves not that mod-squared amplitude equals relative frequency, but only that mod-squared amplitude equals relative frequency with high mod-squared amplitude. Right? But this is not what Everett proved, or what he argued for. He didn't argue that mod-squared amplitude equals relative frequency with high mod-squared amplitude, but that mod-squared amplitude equals relative frequency in nearly all branches of the multiverse, right? According to a reasonable measure of nearly all branches, right? And this is neither conceptually nor technically circular or question begging. It's a statement. It's quite analogous to the statement that the equilibrium state of an ideal gas is Maxwellian. It's not a circular statement. It's like a seminal and extremely profound insight. Of course, here the account looks more circular because it looks like psi square in, psi square out. Right? It looks like we assume psi square is typicality measure, we get outside squares probability measure. Right? But this is really a specialty and a non-trivial feature of quantum mechanics, which is a bit unfortunate from a pedagogical point of view. Right? But in fact, so first of all, the one psi squared weight, right, refers to world branches, right, and is used to give us a notion of what we mean by nearly all or the vast majority of world branches, and is justified by the a priori assumptions or criteria that, that Everett gives us. It's a measure quite analogous to the Liouville phase space measure in classical mechanics. The other psi square refers, the other mod squared amplitude, right, refers to the state in an ensemble of identically prepared subsystems, right? And they correspond to the theoretical frequencies in typical branches, right? It is a measure whose status is analogous to the Maxwellian distribution, which is the velocity distribution for typical microstates, right? And that typical relative frequencies approximate this mod square measure, right? The Born measure in terms of the state of subsystems is not assumed, but derived from Everett's analysis, right? So these, in particular, you couldn't just replace in Everett's analysis user typicality measure with branch amplitudes to the power of 4 and derive a Born rule with amplitude to the power of 4. It wouldn't go through, right? But again, then David continues, well, substitute probability for mod squared amplitude though, and the circularity should sound familiar. Indeed, Everett's theorem, as is well known, is just the law of large numbers transcribed into quantum mechanics. So the circularity in Everett's arguments is just the circularity in the simplest form of frequentism disguised by unfamiliar language. So there are 2 points that I would make here. First of all, justifying a statistical assumption is almost, should finish? Yeah. Right. It's basically always a form of a law. It's always a form of a law of large number. Here we are particularly lucky that we basically get statistical independence for free, but show that statistical independence is preserved well enough by a system of colliding hard sphere to apply the law of large number, and you derive the Boltzmann equation, and you win a Fields medal. Right. So that is always. Justifying a statistical hypothesis is always a form of large number if you want to show that typically empirical distributions are close to a certain theoretical distribution. Right? And really that the account is not circular is, I think, fairly obvious if it doesn't understand it in terms of the simplest form of frequentism, but in terms of typicality, and that's a coin Mario Hubert coined, typicality frequentism, right? So it's not frequentism all the way down, it's frequencies in typical worlds. So thank you very much.
Thanks for the nice talk. So like I was saying that I agree with your overall point that like on the philosophical level, Everett has solved it. That, I mean, in the end, you just needed to define some measure on the set of words, and then from that measure, everything follows. It's essentially the same approach that Simon and Tony Short were doing, but I think it's necessary to emphasize that Everett's proof is mathematically wrong. It doesn't follow from the assumptions that he stated and that you reproduced on the slides. I can show you later why, but it's like just 2 lines derivation.
Okay, yeah, thanks. You should show me if it's really wrong. I looked at it last time. It seems right, so at least easily fixable. But maybe I'm wrong about that. Yeah.
Yeah. Thanks for the talk. So very often we hear that quantum interpretations are really just different stories you tell that all have the same physical predictions as standard quantum mechanics. But in your talk, you show that this is not true. in the sense that if you follow this logic to its end, it would predict some kind of statistical deviation from Born rule statistics. And you say this happens almost all the time, but almost all the time is not all the time. And in particular, physicists have a lot of experience with the statistics of rare events and being able to tease out very rare fluctuations and be able to characterize their statistical properties. And so my question is, first of all, can you use this deviation from Born rule statistics to either confirm or deny one of the two theories? In other words, this is empirically testable. And the follow-up is that, does this argument you have, can you give a mathematically precise definition of how rare this is? In other words, can you put some mathematics to this statement to be able to say, to what kind of statistical precision would you be able to test this in order to confirm one point of view or the other?
No, so on this level of the argument, the situation is really identical to standard quantum mechanics. Also in standard quantum mechanics, if we have the Born rule as a theoretical probability distribution, right, what we actually test or observe are relative frequencies, and relative frequencies typically approach the theoretical probability, and the approximation gets better with larger sample size, but you can also just from the probability calculus estimate fluctuations. So in this sense, the Everett account, the situation is completely analogous to the situation we would have according to standard quantum mechanics and according to any probabilistic prediction, frankly. What is different here is that in an Everettian theory, it also tells us that with certainty, right, there are some future versions of us that will observe very different statistics. And what to make of that, say philosophically, or in terms of what I should expect, or in terms of how I should behave, that I don't know, right? And this goes also into all the issues that Tim raised, that most of us don't seem to act, even if we believe in the many worlds theory, we don't seem to act as if we actually believe in it. So I don't know what to make of this fact that in an Everettian multiverse, there are certainly observers, including future versions of ours, that will perceive arbitrarily large deviations from the Born statistics. But for typical observers, the situation is exactly the same as in standard quantum mechanics.
Thank you. That was a very nice talk, thank you. I mean, it might be worth adding the next sentence in that quote. That simplest form of frequentism may indeed be hopeless, but so far Everettian quantum mechanics has neither helped nor hindered it. And the general point I was making was really, at that point I think you've made very nicely here, in a way I didn't bring out, which is that there's nothing very interestingly different about the way frequentism plays out in the many worlds framework than how it plays out in other frequentist contexts. So if you think the simplest form of frequentism is fine, you should love Everett. If you think you can fix frequentism by typicality arguments, you should love Everett. I'm really skeptical about typicality arguments. I think there's a circularity in these claims about nearly all. They're not cardinality claims. But apply Everettian, I don't mind. I mean, the broader point, I think, is that it doesn't seem to be impossible to identify cases where some particular account of probability works fine in non-Everettian cases, and then that same account breaks in some way in the Everettian case. And I think this is just a really nice illustration that that's true in the Boltzmann typicality construction as well. So thank you.
No, I agree completely. Yeah, I think, of course, I'm very satisfied with like typicality frequentism in the classical sense. And then I think it's a good thing that it carries over to quantum mechanics, be it Bohmian mechanics or Everettian quantum mechanics. And again, I picked out your quote to disagree with it because it's not because I wanted to single you out, of course, but because it's a nice, I think, expression of the circularity worry that is like. But
I don't think you do disagree with my quote. I think your completion, if you like, is indeed there's a circularity in the simplest form of frequentism. Here's a fix, which Wallace does not discuss. That's a perfectly fair point.
Okay, I see.
We can replace. We can.
Yes.
My argument goes on to say, to kick frequentism more and say, therefore, we probably shouldn't be frequentists, but if you are a frequentist, you should be fine with Everett. Your version of my chapter 4 would say, but this is how we fix frequentism, and look, the fix to frequentism is just as good in Everett. You know, your version of my book would spend chapters 5 and 6 explaining typicality frequentism.
Yeah, I see what no, granted, yeah, all right.
Okay, we have to stop here. Thanks very much for that talk.